Okay, so we said spectroscopy, study of radiation after interacting with matter. And we said one of the ways that that matter interacts with radiation is by absorption or stimulated absorption, emission stimulated. So there are two forms of the emission. It can be stimulated or it can be spontaneous. Pardon my beautiful handwriting. And then we said that matter can also scatter radiation because of some inherent properties. So what is it? What is usually studied after the interaction with matter? We study what's left, whether it's in absorption, emission, or scattering. And then there can also be magnetic interaction. Now, so usually when you study, when light shines through matter, and then you observe what happens afterward, there are usually lines to show that an interaction has taken place. So when we're talking about intensity of spectral lines, are you seeing my screen?
No, ma, we can't see your screen.
Okay, just a minute. Okay, so I think the screen is back. So the radiation.
Sorry, ma, we can't see your screen.
Okay, now we can see it, hopefully.
Yes, ma.
So radiation interacts with matter, and then we see what we call spectral lines of different heights and of different and in different positions. So the thing that is often recorded is called a spectrum. We already said that the electromagnetic radiation is made up of a wide variety of wavelengths and frequencies, differing frequencies, same speed, but different frequencies, and which is what we call the electromagnetic spectrum. And the spectrum is divided based on the way it interacts with matter. Some frequencies or wavelengths cause molecular rotation, some cause electronic transition, and some cause vibration of bonds, and so on and so forth. So when we're talking about the intensity of spectral lines now, so what happens after a frequency has been absorbed or taken off? So what I showed the other time, the lines, this is an example. I think, yes, I have an example of a spectrum here. So this is a computer generated simulated, but it is actually similar to what was observed experimentally. So there are actually three lines here. There's this line, there's this very tiny one here, and then there's this line there. So we say that spectral lines have what we call a position and the height. The position is related to the energy. So we know that whatever molecule this is, I think it's a water molecule, absorbs energy of about this frequency, or this energy, absorb photons that have this frequency or wave numbers. They also absorb photons that have that wave number as well. So that's what the position of the lines tell us. They indicate the energy level. Remember, energy level, energy states, that's allowed energies that the molecules can have. And it's something that came from theoretical studies, from quantum theory. Now, the height, that is how tall the lines can be, tells us about how intense that interaction is, how intense that molecule absorbs that energy. The fact that there is an energy separation, remember we represent energy values or energy levels with lines. So the fact that there is a photon corresponding to this difference in energy does not necessarily mean that absorption or emission will take place. So the more likelihood the absorption to take place, then the more intense that transition will be, and the more intense the line will be observed in a spectrum. So taller lines are more intense and are likely to occur, and they tell us how strongly the transition probability or how likely the transition will occur. So what are those things that affect the population of the states? So they affect intensities of spectral lines. Okay, before we go, so I said there's another one here. So there's an energy corresponding to a wave, to a photon here too, but it's not very intense. So we can say that in this range, the molecule absorbs photon of 3.28 times 10 to the power minus 21 joules more than it absorbs the photon of energy 8.24 times 10 to the minus 1 joule. So this one is about 4,000 wave numbers. If you multiply it by the appropriate factor, we get the energy. So the factors that govern the likelihood of transition, so factors governing the likelihood of transition are these basic three things: the population of the initial states, more likely population of where the transition is coming from. So it can be upper state population, in which case you'll be talking about stimulated emission, or it can be the lower state when you're talking about absorption. So this one is an experimental factor: concentration and path length. So concentration of the sample and how big the sample size is. Then there's a third one called selection rules. Let's look at them one after the other. So what is population state? Starts with population of states. Is it moving? Please move. So population of states. From the word population, so existence of molecules in the state. So when we talk about population, you are talking about the number of particles that exist in that state or initial. So let's put it in a better way. So where can I write it? Let me write it here. Population of initial states. So what is population of states? The state is characterized by the energy there. The average number of particles in a state with the same energy E, that's what we refer to as the population of that state. For example, again, energy levels are represented by lines. This is a sample energy levels. This is not representative of all forms of energy levels. That's because some energy levels, they increase in space as you go higher, some reduce in space. But this is just for demonstration purpose. So each state at a certain temperature is characterized by an energy value. Energy level describes states. Once we solve, if you remember from 317, once you solve the Schrodinger equation H psi equals E psi, you get several quantized energy levels. An example of energy level from atomic spectroscopy is the ones that we describe with 1s, 2s, 3s, and so on and so forth. Somebody is chatting. 1s, so 1s state, that's the ground state energy. That is an energy level. 2s is another state. That's an energy level. 2p, 2px, 2py, 2pz. Those are individual energy levels. They are degenerate in hydrogen atom, the 2p and the 2s, but they are not degenerate in other atoms. So when we say population of a state, you're talking about number of particles that have that same energy that you're describing of that state. So once a state is populated, there's a likelihood that there will be a transition from that state. And the more the state is populated, the more likely is for a transition to take place from that initial state. So by default, at 0 Kelvin, that's absolute zero, where the lowest imaginable temperature for molecules, every atom is in the ground state. And the moment you start increasing temperature, they have enough energy to populate higher states. So which means you can have transition from here to here at this stage, but you cannot have transition from here to here, regardless of whether you have the right energy or not. The population of a state is described by this equation right here. The one that we need to know, what we need to note from this equation is that Ni, that's the number of particles, the population of that state in energy E, is directly proportional to G. G is called degeneracy of the state. Degeneracy is how many states have the same energy. It is exponentially proportional to temperature, meaning that as the temperature increases, the lower state, the lower energy state becomes less populated because you have energy to move to a higher state. Okay, one way that I like to describe, or one way I usually like to describe this is, imagine a story building of 6 levels. There's the ground state. The first place is where everybody will be in the ground state, and that will be the population of that state. So the total number of people there will be N. N is the total population. Now, if the place gets crowded, some people have enough energy to move to the first level, and then you have enough population from that state. Now, from that place, some people can still have enough energy to move to higher levels. So you have different states as you go up and up. So degeneracy comes into play when you think about in a floor, you have different rooms. All the rooms are on the same level. So you say that there are different states with different same energy. So different states corresponding to rooms, room 1, room 2, room 3, room 4. So those are different states, but they have the same energy. All are in the ground state energy. If you move to the next one, room 1, room 2, so that would be now room 1, floor 2, room 1, floor, room 2, floor 2, room 3, floor 2. So so you can now call those ones numbers. So likely like quantum numbers. So the key thing that I want it to show here is that the energy, the number depends on the energy of the state. It depends exponentially on the energy. So the higher the energy of the state, the lower it will be populated. However, if you have enough thermal energy, you can move to higher states. So the graph here in this corner, so this is as the energy increases, as this is temperature increasing. At low temperatures, you only have small, you have up to 0.25 populated states populated, but as you increase the temperature, this is temperature increasing, you have higher states with higher energy being populated. Please, our next class, I think I want it to be physical. Q is called partition function. Q is how would I put it? It's not a topic for this class, but it's something that aligns with population of states. Q is just a summary of all possible energy levels that you can have. So for example, in the 6 floors that we mentioned, Q helps to normalize and distribute energies or particles in all the floor as much as possible. You can have Q quantifying rotational, vibrational, or electronic levels, or other types of energy levels that we have already described. KT is called thermal energy per molecule. It's a way to link energy, thermal energy, which is energy at a certain temperature of a molecule with distribution. So key thing here that I want us to look at is that population of the of a state is a function of the energy of the state. It's a function of degeneracy. It's a function of temperature. The more the degeneracy, the more likelihood the state will be populated because there is more place to occupy. The higher the energy, the less likelihood that the state will be populated, but the higher the temperature, then more molecules move to higher states, simply because you have increased thermal energy. And this is explained with our Boltzmann factor. Okay, moving on. This population of states is more useful when we're talking about population ratio. So we said the population of a state is directly proportional to, the degeneracy multiplied by the Boltzmann factor, energy of the state, over kT. So this is when we are talking about per molecule. So if you pick up a different textbook, you may see RT, which is talking about per mole. Anyway, so that's besides the point. So population ratio is the ratio between two states I and J. It's often used to determine absorption and emission intensity. So you're looking at number of molecules in two related system levels, not necessarily with the whole system, because you may not necessarily be interested in the population of a particular state. You just want to know the relative amount of population in this level compared to another level, because that's more related to intensities that we see in spectrum. So, okay, we already talked about degeneracy. Degeneracy is a number of states with same energy. So rotational levels, molecules can rotate, molecules vibrate. Those are energy levels that we're talking about. So I keep on saying this because we're going to keep on talking about them. Then molecules have electronic transitions, and then there's the spin states as well. Okay, rotational motion gives rise to the energy levels that have this degeneracy, where J is called rotational quantum number. So if you are going to be looking at relative population in a rotational spectroscopy, also called microwave spectroscopy, you will need to know the degeneracy of rotational states. How many of us are still there? Also, but for vibrational and electronic states, you are 71 here. Can you write your names in the chat box so that I see? You have 10 minutes to write your names. Any names written after 10 minutes, I'm not going to acknowledge it. 5 minutes, as a matter of fact. Any name written after that, I'm not going to acknowledge it. Because you're about 150. Last class too, I had about 70. I know you will write your friend's name. It's your own palaver. So now this equation, 1, 2, please note it. They are equations that we are more interested in this course than the previous one. The previous one is often when you're dealing with statistical mechanics or when you're dealing with scripting or programming. There's one thing that we learned from this equation. When the spacing between the two energy levels are high, the upper state is rarely populated. We mentioned something similar to that. But when delta E ij, which is the spacing between the two states that you're interested in, when it is small, then you have the states almost all populated. So for example, for electronic, that we already know that the energy level spacing is high, energy for electronic. So you see, it's mostly the ground state that is populated. You still have some more populations for vibrational states. So what you see is that electronic transitions may be more resolved than vibrational or rotational transition. So when we say more resolved, then you don't see as many lines as you would see in rotational. That's correct. Again, the reason why we're talking about population ratios is that it predicts spectral intensities. Higher population, you have stronger spectral lines. If the population of the upper states, so we're assuming that I is lower in energy than J. If population is higher in the upper states, it results in what we call population inversion. So we have two states. We have 1, 2, 3, 4 here, and then you have 1, 2, 3, 4, 5, 6. So here NJ is greater than Ni. So this is a population inversion because we always expect the lower state to be populated. However, this population inversion is essential for stimulated emission, stimulated emission, and it is the basis again of lasers and masers too. The relative intensities helps to understand temperature measurements. Temperature is there. You can always relate intensity, the generations. Once you know what you are studying, and you can calculate the temperature of the system. And it also helps to simplify calculation, especially for those involved in programming. So moving on. Population ratio. There are some things that affect population ratio. Remember, we talked about stimulated absorption, stimulated emission, and spontaneous emission. Stimulated absorption that's the one that the molecule absorbs light and then it is promoted to an upper state. Spontaneous emission, the molecule is in an excited state and it just emits light without external factor. And then in the stimulated emission, the molecule is also in an excited state, but it goes to a lower state with the help of an external radiation or with the help of radiation. So absorption leads to population of the upper states and depopulation of lower states. Spontaneous emission and spontaneous absorption, they both lead to depopulation of higher states and population of the lower states. So there's this guy called Einstein that tries to introduce coefficients that can quantify the probability of these processes. According to Einstein, the rate of stimulated emission, I'm using N and M here because that's what the guy initially used. Are we together or I'm still just by myself? 82 participants now. So stimulated absorption, the rate of stimulated absorption, maybe I should just write rate of stimulated absorption is given by this formula. Then the meaning of all these things are stated. R is called transition moment. So R, transition moment, we'll talk more about it when we talk about selection rules. B called, so B is Einstein coefficient of stimulated absorption. So from this equation, the higher B is, the higher the rate of stimulated absorption. And it's also dependent on rho or energy density of transition. So energy density is also one of these equations should cancel. It's the same, it's just repeated. So so this is just intensity or the intensity of the transition at a particular frequency V. An equation that was derived at the beginning of understanding radiation. So you can have stimulated emission and the rate you can see is the negative. Rate of stimulated emission is like the negative of the rate of stimulated absorption. Then for the third process, the rate of spontaneous emission, we have a different coefficient A. So B represents stimulated emission or absorption. A represents coefficient of spontaneous emission. So total emission rate will be the addition of these two together. So this is total absorption rate and total emission rate. If absorption and emission are taking place, then we know that at that equilibrium, whose phone is somebody is distracting me. Priscilla, please mute yourself. So at thermal equilibrium, so when we say thermal equilibrium, temperature constant, because this is dependent on temperature. The energy density is dependent on temperature. So at thermal equilibrium, the rates of upward and downward transition must balance out. And we can relate spontaneous emission with the stimulated coefficient, this spontaneous coefficient. So why are we looking at this is to tell us that why we are looking at this is to tell us that the population of the state changes frequently. And how does it change? It changes by absorption, emission, and emission. So if you wish to study emission and you're trying to do a stimulated emission, because that's usually often done in the case of Raman spectroscopy and some UV spectroscopy, you would have to take cognizance of spontaneous emission. Spontaneous emission, from here, we say it increases with frequency. So the higher the frequency of the radiation, that's the higher the energy of the radiation or the energy of the photon, the more likelihood you would have spontaneous emission that can greatly affect the population of your upper states. So if you're doing anything with lasers, you would have to put that into consideration. Your intensities will be affected by spontaneous emission. And remember, spontaneous emission is not coherent, and you may not get to record it. Coherent in the sense that it's not in one direction, it goes in several directions. So a little bit of more considerations before we move on to the other thing that affects population of states. So when spontaneous emission is negligible, so when ANM is approximately 0, which will happen at lower frequency based on what we just saw, frequency. So based on what we saw here, coefficients don't increases with a frequency most of the time. When spontaneous emission is negligible, our thermal equilibrium equation reduces to this. And if they are equal, and we can say that this is 0, we can say this is 0, but okay, if the upper state is lower, if the upper state, sorry, M is the lower state, N is the upper state. I think I need to change. If the upper states is lower than the lower states. Let me say that again. If the lower state is more populated than the upper state, a net absorption occurs. If the reverse is the case, and a stimulated emission occurs. And there are times that we are interested in stimulated emission, especially in our laser. If the population are the same, then we say something that is probably no net absorption. One other thing here, if this one is so much, if Nn is much greater than Nm, we can say that we have a population, upper state population saturation. So this is where ANM is approximately equal to 0. That in the situation where we want serious stimulated emission, we can look at the ratio of our spontaneous to stimulated emission rates, which is dependent on the coefficients, equations that we wrote before. Let me write it on the side. Rate of spontaneous emission, spontaneous is minus Nm, N, A, Nm, and rate of stimulated emission, that is minus Nn, Bnm times energy density. Spontaneous emission is not is not affected by energy density because it exists on its own. So if we look at the ratio of spontaneous over stimulated, our Nn cancels out. So we are left with ANM over. So this can be worked out to give this ratio. Again, not the derivative is not the content of this class. So exponential function minus 1, the nature of this exponential function determines if stimulated emission will dominate or if spontaneous emission will dominate. If this is much less than 1, which happens when your energy difference is much greater than kT, stimulated emission dominates. On the other hand, if energy difference is much greater than kT, then spontaneous emission dominates. So if HV is large, which is as the frequency increases, spontaneous emission dominates. Now let me ask a quick question before we move on, and I want to see your answers on the chat box. Based on the electromagnetic spectrum and based on what we have been discussing so far, so what do you think will dominate in the radio frequency region? Spontaneous emission or stimulated emission? Write your answers in the chat box. 2 minutes. Or no, 30 seconds. You're all writing at the same time. I'm waiting. Everybody should write an answer. Again, radio frequency region, what dominates? Spontaneous or stimulated? I hope you're not still going to ask AI. In the exam, you won't have AI. Some of us are already looking out for those of you that want to bring AI, even AI glasses to the exam. Okay, so please let's stop answering. Another one that I want to ask. I want to ask another one. What about in the gamma region? Stimulated or spontaneous? So, okay, please. So for gamma, okay, thank you for those of you that wrote it before it. Gamma for spontaneous. All right. Last question. For last, let me ask. Sorry, can you write your reasons beside it? Gamma spontaneous. Why? Large or small energy? If you want to write for radio frequency to write it, write that's it. All right. So radio frequency, it will be dominated by stimulated. Gamma frequency, gamma region will be dominated, and yes. I'm reading. Yes. Okay, so thank you to all the people that have responded. All right. So let's talk about, so we've talked about population affects intensity. So take home here, population affects intensity. So population of the initial states. So we can't say that it's necessarily population of the lower states. It's population of the initial states that we're coming from. So population and radiative transitions affect population of a state. So we're talking about radiative spontaneous emission, spontaneous and stimulated emissions, and then stimulated absorptions. And then there's an equation that can relate all this, the rate at which this takes place. I know I was supposed to teach from 10 to 11. I actually thought the class was 10 to 11. I think I should have apologized for this at the beginning of the class until the class rep brought it to my attention that it was 9 to 10. And then the 10 to 11 I even started late. Can I quickly run through this one? This one is not as detailed as the previous one, as it's something you're familiar with, so that next class we go to selection rules. Or do you want to call it a day? This one is not plenty. Waiting for your response. Continue with the second part, okay? Anything can happen because ASU can go on strike. So that's the class rep. If the class rep has spoken, class rep has spoken for everybody. Or is there another Gideon in the class? Okay. So the one that we mentioned now, the population of states, of course, that we can conceptualize it, whether it is theoretically or not theoretically, but it makes sense. Okay. The other thing that affects intensity of spectral, of the spectral lines that we see, is the concentration of the sample. So it's concentration of the sample and the path length of the sample. So what we mean by path length, this one I know, I'm sure you're familiar with, but let's just quickly talk about it. So what we mean by the path length is usually you put the sample in a container that is often called a cuvette, and light needs to travel through that cuvette. So if you have a large cuvette, if you have a small cuvette, the concentration will be affected by that. So this is why we say the concentration of path length is a purely experimental effect. We know that once you shine light through any substance, the light that comes out is often less intense. So there's the incident light, and then there's the transmitted light. So the fraction of the incident light that passes through a sample is called the transmittance of that sample at that frequency, and is given by this equation. So it can range from 0 to 1. Oftentimes, it is reported in its percentage, called the percentage transmittance. And the amount of light that is absorbed, so that's the one that is not passed out, is called the absorbance of the sample at that frequency. There's a relationship between the absorbance and the transmitters, and it is a logarithmic relationship given by A equals log minus log T. And since we already put T as I over I naught, where I is a transmitted light and I naught is an incident light, then you have your absorbance given equals log I naught over I. Anyway, there's this two guys here. There's this so that says that the absorbance of light is directly proportional to the distance it's traveled in the sample times how many things are absorbing in the sample. So the higher the number of things that are absorbing, the higher the absorbance. Then the longer the sample, the light passes through the sample, the higher the absorbance. And if you say proportionality, there's always a proportionality constant called the Mosley absorptivity, or something that is not often used, extinction coefficient, with this unit. If we take it back to the equation that we got the other time, log I naught over I, or minus log I over I naught. We have that I, which is the transmitted light, is given by I naught 10 times exponential ELC. So the E is related to how strongly any species absorbs the electromagnetic radiation. Transparent substances have lower extinction coefficients, and opaque substances have higher. Anyway, so back to our intention. The intensity of a line, the intensity of a transmitted light, which is what we are looking at, especially when you probably when you're looking at emission, is it decreases exponentially with increasing concentration and increasing path length. Conversely, if you are studying absorption, the absorbance increases linearly with L, that's the path length, and the concentration. So that's it about absorption and the experimental consideration of absorption and path length. I will share worked examples with you on both concepts that we have looked at. The last thing on population, intensities, intensity, we've talked about population of initial states, and now we are talking about the concentration, an experimental part, concentration, and path length. Now, in some textbooks that are dealing with the basic theory of molecular spectroscopy, not the experimental part, you may or may not see concentration and path length. It doesn't mean that they are wrong. It just means that the focus of that text is the theoretical concepts. So the other one, very, very theoretical. It's not abstract. It's just theoretical. When you're looking at anything, you try to rationalize it. Is the other thing that affects it, other than population and its concentration, is selection rules. Meaning that you may have enough population in the initial state, you may have the right energy, you may have enough light to shine on the sample, and your absorption path length gone might be very, very long, such that you have enough time for you to have absorbed the light and still nothing takes place. Now, this is where the concept of selection rule comes in. A selection rule or a transition rule is a rule that determines whether or not a transition can occur within a certain frame. Before I go into too much of the details of it, consider somebody in SS1 going to SS2. The condition is that regardless of whether the students are paid, I think the most expensive school in Lagos now, I think you pay about 22 million. So even if the students are paid 22 million, it is still required that, I'm just saying, that the students must pass 5 subjects, including maths and English, before you are promoted to SS2. So the selection rule takes care of that. So regardless of whether you have paid the 25 million or whether you have attended class from the beginning, that's even true. Those of you, this is something that you students do a lot. When results come out, you will write one beautiful love letter. Dr. Winu, you always see me in class, and I was always sitting in front and even answered your question. But at the end of the day, I scored 42. It is not me. It is what you wrote down. So these are the things. If you do not write what you are supposed to do, the selection rule, which is the marking scheme in this case, will say it is 0. If it is allowed, then it is allowed. So let's come back to class. A selection rule or a transition rule determines whether a transition will occur or not. So emphasis on something here, it's a quantum mechanical rule. Remember, we said energy levels are obtained from solution to our almighty Schrödinger equation. Looks very simple, but it can be extremely very complicated. So there are different equations that govern rotational motion, vibrational motion, electron transition, translational motion, even spin motion. And you can get several energy values. Now, this psi, let's move on. I think I have some fascinating equations, hopefully fascinating to you. Excuse me. So, the origin is from this thing right here, transition dipole moment. It's related to the R that I said we're coming to the other time. And when I said, what's it again? Excuse me. So I said R was a transition moment that affects, that's the Einstein coefficient is dependent upon. Okay, so this one is a transition dipole moment from state 1 to state 2. State 1 is characterized by this wave function. State 2 is characterized by this wave function. What is a wave function? Recall, wave function is the mathematical description of a state, an atom, a molecule, or all these little particles. Interestingly, the truth of the matter is you and I, we all have our wave functions. It's just that they are very complicated to derive. So the thing about wave functions is that, let me write it in a cleaner space. They contain all the information about the particle. For example, as a human being, the human being that you are, if I want to know anything about you, you actually have that information, whether you know it or you don't know it. For example, I know you don't know your weight of head, but it is you that can still get it. All I need to do is put you on a scale and then I'll get it. So that's why I said each person has its own wave function. So now back to class. There's this operator here. We call it the transition dipole operator. Once we integrate all this together, we get a numerical value. The closer the value is to 0, then the closer to the interaction being forbidden. The higher the value, the farther away it is from 0, the more intense the transition is. So let's recap what we are saying. A selection rule is a quantum mechanical rule that determines whether a transition will occur or not. Each molecular state is governed by its own wave function. So there's a transition integral that once you carry out that integration, you can say whether a transition will occur. So we've written it here. It's a transition, is a dipole moment operator. What has that got to do with electromagnetic radiation? It has everything to do with it because the electromagnetic radiation has a dipole moment attached to it. So yes, the electromagnetic has an electron component to it, and the molecule has an electric or a magnetic dipole. So the interaction of that radiation is what results into this equation. Now, I'm just showing this equation. I do not expect you to go and derive that equation. That is probably a 2-semester long of maybe not 2 semesters, but at least a semester. So it is just to show you that there's something called a dipole transition operator that operates on the 2 states, and the value determines whether you will get a transition. So this moment, like I wrote here, represents a transition dipole induced by electromagnetic field, and it only exists while the radiation interacts with the molecule. Once the radiation stops, this is, of course, it no longer exists. Now, if this is not equal to 0, then the transition is allowed. If this is equal to 0, our transition dipole moment integral, if it's equal to 0, then we say the transition is forbidden. Excuse me. So repeating again, allowed transition, they have more intense, they have large mu z. So it's not like it's a value of 1 or 2. It's just that you have higher values, then you have more intensity. So the larger the mu z transition, the transition dipole moment integral, then the stronger the spectral line. So that's the key word for us in selection rules. In population, the larger the population of the initial state, the more likelihood transition will take place, meaning that the more likelihood the spectral line will be. For the experimental one, the more the concentration, the more likelihood you will see an absorbance, and the less likelihood that you see the line transmitted. Now, let's talk about these forbidden ones. We said that so that is when mu z12 equals to 0. Does it mean that it will never occur? Not necessarily. But we know that but if it is ever going to occur, it's going to have low probability or very low intensities. Let's go back to our situation of the boy that has paid 24 million and has failed. So out of the 5 subjects, he passed 4, and then the 4th subject, he didn't completely fail it, but he got something like, not a good grade. Somebody can now say that, let us consider maybe the boy has clinical or this and that. You see, it's with low intensities, but it's forbidden, which means it's not allowed, but it may still occur. Anyway, so meaning physical is that only transitions that lead to a net dipole moment. Remember, we said that this transition dipole represents the interaction of the electromagnetic radiation with the inducing dipole moment in the molecule. So in real molecules, like I said, forbidden transition will still occur. In real molecules, forbidden transition occur weakly due to something called vibronic coupling. Remember when we were talking about Born-Oppenheimer approximation, we said that we can I did not use the word absolute. We can separate these motions from one another, vibrational, electronic, and rotational. But you still have some overlap areas. So that's where coupling comes in. Same thing, it's still the same kind of coupling. The spinning motion, that's the one that leads, you're talking about rotational. Rotational is a spinning motion about its center, and then you can have some orbit motion complex with it. So a little bit of asymmetry. Molecules that don't have permanent dipole, they are usually very symmetric, and they tend not to absorb some kind of electromagnetic radiation. But if you introduce some asymmetry, maybe due to asymmetric stretching, you would have something going on. So can we say that there's selection rule generally for all spectroscopy? No, each type of spectroscopy has its own selection rule. So this is the last slide for today. This one that I want to talk about. So there are 2 types of selection rule that you can talk about. You can talk about the gross selection rule and then the specific selection rule. So the gross selection rule talks about the general properties that the molecule should possess. So in such a situation, you say that the kind of molecule that you can study with this spectroscopy. So the kind of molecules that you can study with microwaves spectroscopy, the general selection rule says that they must have a permanent dipole. So for example, give me an example of molecules with permanent dipoles. Just type it. Diatomic molecule. Can you just type examples of molecules with permanent dipole, please? Waiting. Because I've had a class where somebody asked me, how do I know a molecule has permanent dipole? So a molecule that has a permanent dipole moment is a polar molecule. So I'm giving you another thing. So please type molecules, their formulas, please, of molecules that are polar. While we are doing that, let me drink something. Go on, go on, go on. So H2O, H2O. CH, somebody wrote CH2Cl2. Is it polar? Oh, I think it is. That's true. CH4 is not polar. So we cannot study molecular spectroscopy. Oh, sorry, we cannot study CH4. Emmanuel Ajibike, what is polar? CH4 or which one? Please, you can unmute yourself and or you can type your answer. Oh, okay. Dichloromethane. Yes, it's polar. The first thing that came to my mind when I first saw it was C2H2Cl2. Yes, CH3Cl is also polar. Oga, okay. Omolabi Iwelari. So, again, but some people can still argue that there's a way you can. CH4 is not polar, which means by default you won't want to use microwave spectroscopy to study it. But some people will tell you that if you can introduce some asymmetry into it, so you make one bond longer, so you introduce some polarity, you'll be able to study it. But hey, that doesn't make any economic sense. So the next one, I will not go through. The next one involves a change in dipole moment, the vibration. So that thing, we often call it a dynamic dipole moment. The molecule must possess a dynamic dipole moment, meaning that as vibration is taking place, there must be an induced dipole moment. I think I'm going to leave that definition to Dr. Akibulu, or I can just quickly mention it. Once you are doing once the vibration is taking place, there must be a change in dipole moment. I think I have space. For example, let's look at this. CO2 is not polar. But if I stretch this bond, that's called asymmetric stretching, and compress this bond, then that is the dissimilarity, asymmetry in charges, and this stretching becomes this stretching makes the molecule to have a temporary dipole moment. So that's what we say a dynamic dipole moment. It's not that the molecule is polar, but the vibration itself introduces some form of dipole moment. So Raman, you must have a change in polarizability. Electronic spectroscopy, you can study any form of molecule with it. So nuclear magnetic, active magnetic nucleus, and unpaired. This one requires unpaired electrons. So that's, again, gross selection rule is related to the general properties that a molecule should possess. On the other hand, specific selection rule is related to the quantum numbers that describe the state, the molecule. Electronic transition. So this is for atoms. Electronic states are characterized by L, M, L, S, and there's one that I didn't include, the principal quantum number. So delta N can be anything for electronic transition in atoms. I have not included the ones for molecules here. This is just to show us what we are talking about. Rotational states are characterized by J and M sub J. Vibrational states are characterized by V. So the specific selection rules says the allowed states, allowed changes that can accompany the selection rule that characterizes the molecule. So these rules are essential in predicting and explaining spectral lines and also spectral line intensities that are observed in spectrum. So last thing before, I think I just have the table to show that. So last thing before we go, what are the things, your answers again, what are the things that affect intensities of spectral lines? Mention the three, and then we can call it a day. That's the summary of what we have talked about. What are the things that affect the spectral lines? Intensities of spectral lines. Only one person has. There are three things. You are only mentioning one thing. Another question, what processes lead to the population of the lower states? Which radiative processes lead to the population of the lower states? What is in it? So for those of you that are providing answers, please, more appropriately, population of the initial state is the one that affects the intensity. It's not necessarily, thank you, Emmanuel. It's not necessarily the population of states. So it's population of the initial states that leads to spectral line intensities. Okay, now there's an answer here. Low energy is not a process. It's an observation. So the question was, which processes lead to population of the lower states? So like somebody rightly wrote here, stimulated what? Joker. Are you joking with me? You said stimulated leads to population of low states. That's a better one. Stimulated emission. Your name says Joker now, so it's a who knows. So stimulated emission, that's what everybody's writing. So it's stimulated emission and spontaneous emission will lead to population of lower states. please practice writing complete sentences. If you say you are writing stimulated emission will lead to a lower state, no, it leads to population of the lower state. Once you start practicing it, you get used to it, so that you won't need to write love letter to me at the end of the semester telling me that you were always answering a question in class, yet you did not get A. You remember the selection rules then? All right. So I'll see you all on Thursday. Thank you. Or any question? Let me not be a terrible teacher. Any question?
Sorry, ma. Thanks for today's class, ma. Please, are we going to get the slides and the recorded class?
I'll think about it. You are supposed to be in class and take notes now.
Ma, we couldn't take note of everything, no. And we actually needed to revise.
You are Gen Z. You are supposed to be blazing fast.
I know my job.
Wait, I hope I tried to record it, sir. Let me see. It's still recording. Hold it in, Joe. If I did not record it. Okay. See you next class. Any other question? My voice wants to be. Okay.
Ma, please, the recorded class.
The recorded what in here? I will see what I can do about it.